In this video, we'll learn how to solve problems in Principle of Mathematics Induction. Now, I want you to know that to solve problems in mathematics inductions, the steps you need to take is just 3 simple steps. Step one, you need to prove that n is equal to 1 is true. For step 2, you need to assume that n is equal to k is true. Step 3, you need to show or prove that n is equal to k plus 1 is true. Okay, so if you can take a mathematical statement like this through these 3 steps, it can be verified by Principle of Mathematics Induction that the statement is true. So for the first step, n equals to 1 may not necessarily be 1, but it is the first term in the sequence. Okay, the first term in the set of natural numbers. So in this case, n equals to 1, the first term will be start from 2. If we plug in values less than 2 here, this statement will not be correct. Okay, so let's quickly solve this problem. So for the first step, for step 1, we know that p of 2 should be true, right? So p of 2, that's statement of 2, we could say 1 minus 1 over 2 squared already, okay? And then this is equal to 2 plus 1 over 2 times 2, right? Okay, so from here we know that 1 minus 1 over 4, okay? And then on this other side we know that 2 plus 1 is 3, and then 2 times 2 is 4. So on this other side, we know that 1 minus 1 over 4 is 4 minus 1 over 4, and then this is equal to 3 over 4. So 4 minus 1 is 3 over 4, and then this is equal to 3 over 4. Okay, so we've proven that p of 2 is true. The next step is to assume that p of k is true. So for step 2, we assume n is equal to k. Okay, so we basically have to rewrite this statement. So this statement is saying 1 minus 1 over 2 squared times 1 minus 1 over 3 squared on up to, you have 1 minus 1 over k squared. So we are simply going to be replacing the n's with k's. So this is equal to k plus 1 over k 2k. Okay, so for the next step, for step 3, we show n is equal to k plus 1 is true. Okay, so we already have our kth term here. So for our next term after our kth term, we would have, let's write the sequence again. So this is 1 minus 1 over 2 squared dot, and then we have 1 minus 1 over 3 squared, and then on up to our kth term, which is 1 minus 1 over k squared. Okay, so for our k plus 1 term on this part, we know that this is equal to 1 minus 1 over k plus 1 squared. Okay, so from here on, we know that this is equal to k plus 1 plus 1. Okay, so this is now 2 open brackets k plus 1. Okay, so let's simplify this expression to prove that this is equal to this. So before we simplify this, it is worthy to note that these parts, initially we wrote something like this: 1 minus 1 over 2 squared. From the second step, we wrote this. So this is 1 minus 1 over 3 squared. And then this is 1 minus 1 over k squared. And then this is k plus 1 over 2k. So we know that from all these points, all of these points can be replaced with this. Okay, so we can simply pick this and plug it into these parts. So that would give us k plus 1 over 2k. Okay, k plus 1 over 2k times the next term, which we are not replacing. And then this is 1 minus 1 over k plus 1 squared. Okay, so this is equal to, we know that k plus 1 is k plus 2, and then over 2 open bracket k plus 1. Okay, so let's clean up space. So if we can simplify this by multiplying through by these two terms. So if we apply through by these terms onto these ones, we have k plus 1 over 2k minus k plus 1 over k plus 1 squared times 2k. Okay, so we know that k plus 1 can cancel out k plus 1 from that here. So this is equal to k plus 2 over 2 open bracket k plus 1. Okay, so let's clean up extra space. So from here we have k plus 1 over 2k minus 1 over k plus 1 2k. Okay, so from here on, this is equal to k plus 2 over 2 open brackets k plus 1. So we can simplify this further. We know that LCM here is 2k. Let's clean up the extra space on the bottom. So you can simplify this further by saying, we know that the LCM is 2k open bracket k plus 1. Okay, so this is k plus 1, and then if 2k open bracket k plus 1 divided by 2k is k plus 1 times the already existing k plus 1 there. Okay, so this divided by this is nothing, so it's 1 basically. So plus 1 minus 1 minus 1, and then this is equal to k plus 2 over 2 open bracket k plus 1. So to simplify this further, we know that expanding this bracket becomes k squared plus 2k minus 1 minus 1. Okay, so minus 2k open bracket k plus 1 is equal to k plus 2 over 2 open bracket k plus 1. So we still need to clean up space. So from here on out, we know that for the numerator of this is k squared plus 2k. 1 minus 1 is 0. So this divided by 2k open bracket k plus 1. Okay, so k can be factorized from here. If k is factorized, we have k open bracket k plus 2. And then here we have 2k open bracket k plus 1. Remember, this is equal to k plus 2 over 2 open bracket k plus 1. And then this is also equal to k plus 2 over 2 open bracket k plus 1. So let's clean up extra space. So we have from here, we factorize k here, so k can cancel out 2k here. So this becomes k plus 2 over 2 open bracket k plus 1, which is equal to k plus 2 over 2 open bracket k plus 1. So we've proven that for the n equals to k plus 1 term, this statement is true. So we've used Principle of Mathematical Induction to validate this statement. So let's quickly take another example. Okay, so like we did before, we're simply going to use the same idea for the previous ones. But if you notice, there are no restrictions to our n value here. So when there are no restrictions, you simply start from n is equal to 1. Okay, so from the first natural number. So let's quickly take our steps for the Principle of Mathematical Induction. So for the first step, we need to show that n is equal to 1 is true. Okay, so we are simply going to be plugging n equals to 1 here. Okay, so for n equals to 1, right? So for the first term here, this is 1. Okay, so we know that this 1, and then this equal to, for this other part, we know that 1 squared is 1 is equal to 1. So we've shown that the left hand side at n equals to 1 is equal to the right hand side. So assume n is equal to k is true. Okay, so if you assume n equals to k is true, this whole statement will change. So 1 plus 3 plus 5 open bracket 2k minus 1 is equal to k squared. So you need to take note of this statement because you're going to use it for the third step like we did before. So for step 3, we need to show that n is equal to k plus 1 is true. Okay, so we write this statement by saying 1 plus 3 plus 5, and then we know that this statement simply shows the nth term of this sequence. Okay, so this statement is the kth term, 2k minus 1. So for the next term after 2k minus 1, that will be plus, because the sequence has a plus here. So that will be plus open bracket 2 open bracket k plus 1, okay, minus 1. And then this is equal to, we are simply going to plug in our k plus 1 directly into n squared. So this is k plus 1 squared. So now we have to show that the left hand side of this equation is equal to the right hand side. So to do that, we know that looking at equation step 2 and then at step 3, we know that this part of our equation in step 3 is equal to k squared, like we got from here. So this part is equal to k squared. So we are going to be replacing this part with k squared. So this is k squared plus open bracket 2 open bracket k plus 1 minus 1, and then this is equal to open bracket k plus 1 squared. Okay, so k squared plus 2 times k is 2k plus 2 times 1 is 2, and then minus 1 here. Okay, so this on the right hand side we still have our k plus 1 squared. So if you simplify this further, you'd have k squared plus 2k plus 1, and then this is equal to k plus 1 squared. So if you factorize this, you should be getting k plus 1 squared, and then this is also equal to k plus 1 squared. So we've shown that n is equal to k plus 1 is also true. So we've solved this problem and proven that this mathematical statement is true from the principle of PMI. So let's take another example. I have a mathematical statement of 3 plus 7 plus 11 plus, and then we have on up to the term that defines the sequence 4n minus 1, and then this is equal to n open bracket 2n plus 1. So basically, I want you to pause the video and try to solve this one yourself. Okay, so like we did before, to get our first term, we assume that n is equals to 1 automatically. Okay, so if we say for step 1, when n is equal to 1, so the first term here is the n equals to 1. The first term here is 3. So P of 1 is 3. Okay. And then for the right hand side of the equation, we know that 1 open bracket 2 open bracket 1 plus 2 plus 1. So we know that 3 is 1 times 2 times 1 is 2 plus 1. So we know that 3 is equal to 3. So 1 here, n is equal to 1 is for the first term here. N is equal to 1 is always for the first term of the sequence. But you can also get n is equal to 1 by plugging 1 directly into this linear equation that can give you any term on this stuff. So you can just plug n equals to 1 for the first term here, okay? But you can also pick it directly from the sequence. So this is 3, okay? And then if you pick n equals to 1 here, you still have 3, okay? But let's say you have n is equal to 4 or something. You want to prove that n equals to 4, but you might not need to prove it. But just in case, you'll be saying 4 open brackets, 4 plus 4 times 4 is 16. 4 open bracket, 4 times 4 is 16 minus 1. So this should be equal to 15. So if you add up these terms, they are more than 15, but the fourth term here is 15. Okay, so this simply gives you the term value, not the sum of the values. And then this equation defines the sum of the values. So that's why we have to pick them directly from here. Okay, so let's go to step 2. For step 2, we assume n is equal to k, right? So you are simply going to be replacing all n's here with k. So this will be 3 plus 7 plus 11 plus, and then on up to open bracket 4k plus 4 minus 1 is equal to k open bracket 2k plus 1. Okay, so you need to take note of this relationship here. Okay, so for step 3, we need to show that n is equal to k plus 1 is true. So to do that, we simply write out our terms out. So this is plus 7 plus 11 plus on up to our kth term, which is 4k minus 1. So for our k plus 1 term here, this will be plus 4 open brackets 4k plus 1 minus 1. Okay, so this is also equal to, on the right hand side, we simply plug k plus 1 for n values. So this is k plus 1 open brackets, so open bracket k plus 1 plus 1. Okay, so we know that from this part to this part, we can replace this part with this from our assumption number from our step 2. Okay, so to replace this part with this, we know that k open bracket 2k plus 1 Then the next term here is plus 4 open bracket k minus 1, k plus 1, and then minus 1. And then this is equal to k plus 1 on the right hand side. Simplifying this with simplifying this bracket here, you have 2k plus 2 minus 1. Okay, so let's clean up space. So if you simplify this further, you have 2k squared plus k, and then plus 4k plus 4 minus 1. And then this is equal to k plus 1. Okay, and then for this part you have 2k plus 1. Okay, so if you simplify this again, you should have 2k squared plus 5k minus 3 plus 3, and then this is equal to open bracket k plus 1 and 2k plus 1. So from here, if you were to simplify this bracket, if you were to factorize this bracket, you get open bracket k plus 1, okay, 2k plus 1. And then this is equal to k plus 1, 2k plus 1. So that's the proof for this statement is equal to this statement. So the proof is simply true. So if you like this video, you can share with your friends. You can also subscribe and leave a thumbs up. It helps the channel. Thanks for watching.